Hello friends, I welcome you in lecture number 7 on infinite series. In this lecture we will discuss about limit comparison test. In previous lecture we have seen direct comparison test. So this is another comparison test known as limit comparison test. So in limit comparison test, suppose we are given to check the convergence of some positive series. Positive series means an is greater than 0 for all n, and suppose there exists another series with positive terms, say sigma bn. So sigma bn is also a positive series such that limit of an upon bn as n tends to infinity equal to say c. So in limit comparison test, suppose we are given some series sigma an, we will select another series sigma bn, and then we will find out limit of ratio of nth term of sigma an to the nth term of sigma bn, that is limit of an upon bn as n tends to infinity. So suppose value of this limit is L. So depending upon the value of this limit C, we have different cases. So now an is a series with positive terms, bn is also a series with positive terms. That means an upon bn is also positive for all n. So that implies that this limit is either positive or it can be 0. So there are three possibilities: either c is positive or c is 0 or c can be infinite. So if c is positive, then if our series which we have selected is convergent, then given series is convergent, and if series we have selected is divergent, then given series is divergent. I repeat again, if limit of an upon bn as n tends to infinity, which is c, so if this c is positive and finite, then the behavior of sigma an is same as the behavior of sigma bn, that is sigma an and sigma bn either converge or diverge simultaneously. So if our series selected is convergent, original series is convergent, and if selected series is divergent, original series is divergent. And second possibility is c equal to 0. So if c equal to 0, then if selected series is convergent, if sigma bn is convergent, then sigma an is convergent. And if c is infinite, then if sigma bn is divergent, then sigma an is divergent. So this is the limit comparison test. We have written this limit comparison test here. Suppose that sigma an and sigma bn are series with positive terms. If limit of an upon bn as n tends to infinity equal to c, where c is a finite number and c is greater than 0, that is c is positive and finite, then sigma an and sigma bn both converge or both diverge. That means if sigma bn is convergent, sigma an is convergent, and if sigma bn is divergent, sigma an is divergent, if this limit is finite positive number. Now if limit is 0, then if sigma bn is convergent, then sigma an is convergent, and if limit is infinite, then if sigma bn is divergent, sigma an is divergent. So we understand this with the help of these examples. Discuss the convergence of following series. We start with first series. First series is given as 3 by 4 plus 5 by 9 plus 7 by 16 plus 9 by 25 and so on. So here we have to first write down this series in sigma notation, or we have to decide the general nth term of this series. So we can see in the numerator we have 3, 5, 7, 9 and so on. So this becomes the arithmetic progression with first term a equal to 3 and difference equal to 2, and we know that if we have arithmetic sequence, then its nth term is given by a plus n minus 1 into d. Here a is 3 and d is 2, so a plus n minus 1 into d, which is 2. So this is 3 plus 2n minus 2, so it becomes 2n plus 1. So in the numerator we will write down 2n plus 1. When n is 1 we have 3, when n equal to 2 we have 5 and so on. Now in the denominator, in the first term we have 3 by 4. So we can write 4 as 1 plus 1 whole square, that is 2 square. Similarly we can write 3 as we can write 9 as 3 square, which we can rewrite as 2 plus 1 whole square. Similarly 3 plus 1 whole square is 16. So this 4 is corresponding to n equal to 1, and we have written 1 plus 1 whole square. 9 is corresponding to n equal to 2, which is written as 2 plus 1 whole square. 16 is corresponding to n equal to 3, which we have written as 3 plus 1 whole square. So in general, the terms in the denominator can be written as n plus 1 whole square, and in the numerator we have 2n plus 1. So from this we have the idea that nth term is given by 2n plus 1 over n plus 1 whole square, and this we expand here. So we have sigma 2n plus 1 over n square plus 2n plus 1. So this is the sigma notation for given series. So we have written nth term of this series. Now if we want to apply limit comparison to this type of series in which we have only powers of n, that is in the numerator we have polynomial function in n, and in the denominator we have another polynomial in n. So if nth term is division of polynomials in variable n, then to select our series Bn, we find out highest powers of n in the numerator and denominator. In the numerator, highest power of n is 1, so here we consider n, and in the denominator highest power of n is 2, so here we consider n square. So this is 1 by n. So we will select Bn equal to 1 by n. So whenever we are applying limit comparison test, and if our nth term is division of polynomials in variable n, then we will select Bn in this way. So here we consider Bn equal to 1 by n. So we can see that Bn is also positive for all n. So sigma an and sigma bn are both positive series, so we can apply limit comparison test. So now we take limit of an upon bn. An is 2n plus 1 over n square plus 2n plus 1 divided by 1 by n. So in the next step, this 1 by n, if we take in the numerator, it will multiply with 2n plus 1. So that is 2n square plus n divided by n square plus 2n plus 1. So here to find out this limit, we can observe that this is infinity by infinity form. So either we can apply L'Hospital rule, or we can divide numerator and denominator by highest power of n. Here highest power of n is n square, so we divide this as well as this by n square, and we obtain that 2n square divided by n square, which is 2, plus n divided by n square, which is 1 by n. Similarly here 1 plus 2n by n square, which is 2 by n, plus 1 by n square. Now if we consider limit as n tends to infinity, this is going to be 1 by infinity, which is 0, these two terms are also 0, and because limit of constant term is constant, we have 2 plus 0 divided by 1 plus 0 plus 0. So limit of an upon bn as n tends to infinity is 2, which is positive and finite. So now we concentrate on the selected series. Selected series is sigma bn, which is nothing but sigma 1 by n, and this is harmonic series. We know that harmonic series is divergent because it is a p series with p equal to 1, and p series is convergent only if p is greater than 1. So now sigma bn is divergent, and this limit of an over bn as n tends to infinity is positive and finite. Therefore, by limit comparison test, sigma an given series is also divergent. So here we are applying first part of the limit comparison test, which says that if limit of an upon bn is positive and finite, then sigma an and sigma bn both converge or both diverge. So here sigma bn is divergent, therefore sigma an is also divergent by limit comparison test. We consider second series. It is 1 plus 1 by 3 plus 1 by 7 plus 1 by 15 and so on. So we can write this in sigma notation as, we can observe that if we consider 1 over 2 raised to n minus 1, then we will obtain all these terms. When n is 1, we have 2 minus 1, which is 1. When n is 2, we have 2 square minus 1, that is 4 minus 1, which is 3. When n equal to 3, we have 2 raised to 3, which is 8 minus 1, 7. So this is sigma notation, and nth term is 1 over 2 raised to n minus 1. So now we have to decide that this series behaves like which series. So as we consider n tending to infinity, or for large n, this series will behave like 1 over 2 raised to n. So we can consider bn equal to 1 over 2 raised to n is greater than or equal to 1. So bn is positive. Given series is also positive for every n. So now we find out limit of an upon bn as n tends to infinity. An is 1 over 2 raised to n minus 1. This is bn, and this we can rewrite as limit of 2 raised to n divided by 2 raised to n minus 1, and then we divide numerator and denominator by 2 raised to n. So 2 raised to n divided by 2 raised to n, which is 1. Here also we divide by 2 raised to n, so we have 1 minus 1 over 2 raised to n. And if we consider limit as n tends to infinity, limit of 1 is 1, here limit of 1 is 1 minus 1 over 2 raised to infinity. 2 raised to infinity is infinity, and 1 by infinity is 0. So limit of an upon bn here also is positive and finite. Now our series which we have selected is sigma bn equal to sigma 1 over 2 raised to n equal to 1 to infinity. So if we expand this, we have 1 by 2 plus 1 by 2 square plus 1 by 2 raised to 3 and so on. So this is a geometric series with common ratio r equal to 1 by 2, and absolute value of r is less than 1, and we know that geometric series is convergent if absolute value of r is less than 1. So therefore sigma bn is convergent, and therefore by the limit comparison test given series is also convergent, and this was the given series. So this series is convergent by the limit comparison test. Next example, log n divided by n raised to 3 by 2, n equal to 1 to infinity. So here nth term is log n divided by n raised to 3 by 2. Now to apply limit comparison test, we should select proper Bn. We should select proper series sigma Bn whose convergence or divergence is known to us. So to select that proper series, we have to use this logic. We can check for sufficiently large n, logarithm of n is less than 1 by 4th power of n or 4th root of n. So natural logarithm of n is less than 4th root of n for n sufficiently large. And here in the division we have n raised to 3 by 2. So we consider division by n raised to 3 by 2 on both sides. So we obtain log n divided by n raised to 3 by 2 is less than n raised to 1 by 4 divided by n raised to 3 by 2. And this we can simplify as 1 over n raised to 3 by 2 minus 1 by 4. We consider n raised to 1 by 4 as 1 over n raised to minus 1 by 4, and this is n raised to 3 by 2 minus 1 by 4. Now 3 by 2 can be written as 6 by 4, and 6 by 4 minus 1 by 4 is 1 over n raised to 5 by 4. So from this we have the idea that we should select Bn equal to 1 over n raised to 5 by 4. So we take Bn equal to 1 over n raised to 5 by 4, and now we calculate limit of an over Bn as n tends to infinity. So we substitute values of an and Bn, and we can rewrite this as log n over n raised to 3 by 2. If we take this in the numerator, we have n raised to 5 by 4. This again we can rewrite as log n divided by n raised to 3 by 2 minus 5 by 4. And again after simplifying, 3 by 2 can be written as 6 by 4. So after simplifying we have log n divided by n raised to 1 by 4. Now if we consider n tending to infinity, we have log infinity, which is infinity, and infinity raised to 1 by 4 is also infinity. So this is infinity by infinity form. So we can apply L'Hospital rule. So we take derivative of log n and n raised to 1 by 4 separately. Derivative of log n is 1 by n. Derivative of n raised to 1 by 4 is 1 by 4 times n raised to 1 by 4 minus 1, which is n raised to minus 3 by 4. And if we consider, we write this as 1 by n into 1 over n raised to minus 3 by 4. This 1 over 1 by 4 is going to be 4, which we have taken outside limit, and this we can rewrite as 1 over n raised to 1 minus 3 by 4, and 1 minus 3 by 4 is 1 by 4. So finally we have 4 times limit of 1 over n raised to 1 by 4, and this is equal to 0. So in limit comparison test we have three parts, and here we have the case that limit of an upon bn is 0 as n tending to infinity. So if our selected series is convergent, then given series is convergent. Now selected series is sigma bn equal to sigma 1 over n raised to 5 by 4, and this is p series with p equal to 5 by 4 greater than 1. So it is convergent, and therefore by the limit comparison test sigma an is also convergent, and this was the series sigma an. So in this example we have used this logic to decide the selection of series Bn, log n is less than n raised to 1 by 4 for large n. So using this we are able to decide that Bn which we have selected was 1 over n raised to 5 by 4. Next example, series is 1 plus 2 log 2 divided by n plus 1 plus 3 log 3. These are the different terms of the series. 1 plus 3 log 3 divided by 14 plus 1 plus 4 log 4 divided by 21, which we can rewrite as 1 plus n log n divided by n square plus 5. Series is starting from n equal to 2. For n equal to 2 we have 2 square which is 4 plus 5, that is 9. For n equal to 3 we have 3 square which is 9 plus 5, 14, and so on. So this is the nth term of given series, 1 plus n log n divided by n square plus 5. Now again the problem is how to select proper series sigma Bn. So for that we have to examine or we have to check the behavior of this series. So for large n we can assume that this series will behave like this series, n log n divided by n square, which is nothing but log n divided by n. And again for large n this will be greater than 1 by n for large n. So from this we have the idea that we should select Bn equal to 1 by n. So here we have written for large n we expect an to behave like log n by n, which is greater than 1 by n for n greater than or equal to 3. Value of this is greater than 1 by n if we consider n starting from 3 and for every n starting from 3. So we select Bn equal to 1 by n and then we take limit of an upon Bn. So limit of an upon Bn as n tends to infinity. This is an, nth term 1 plus n log n divided by n square plus 5 divided by 1 by n. So this we can rewrite as this 1 by n. If we take in the numerator it will multiply with 1 plus n log n, and if we multiply, okay, we keep this as it is, 1 plus n log n divided by n square plus 5, and 1 over 1 by n is n. Now we divide numerator and denominator by n square. So here we divide n times 1 plus n log n by n square. So we write n square as n into n. So 1 n will cancel out here, and we have 1 by n plus log n, and here 1 plus 5 by n square. So now if we consider limit as n tends to infinity, this is going to be 0 because we have infinity in the denominator. Here also 5 by infinity is 0. Here we have log infinity and the limit of 1 is 1. So limit is log infinity, which is infinity. So limit of an upon bn as n tends to infinity is infinity. And the series which we have selected is divergent, and limit comparison test says that if limit of an upon bn as n tends to infinity is infinity, then if selected series is divergent, given series is also divergent. So therefore by the limit comparison test, sigma an is also divergent. And now we consider last problem. This is simple. Here our series is sigma n plus 1 over n cube minus 3n plus 2. So here we have an is division of polynomials in n. So we select bn as, here in the numerator highest power of n is 1 and in the denominator highest power of n is 3. So from this we have the idea that we consider bn equal to 1 by n square. So we take bn equal to 1 by n square and then we consider limit of an over bn as n tends to infinity. An is n plus 1 over n cube minus 3n plus 2 and 1 by bn, that is n square. So here we multiply n plus 1 with n square and we have n cube plus n square divided by n cube minus 3n plus 2. Now we divide numerator and denominator by n cube. So we have 1 plus n square by n cube is 1 by n. Here 1 minus 3 by n square plus 2 by n cube. And if we consider limit as n tends to infinity, we have 1 plus 0, that is 1. Here also 1 minus 0 plus 0, which is 1. So limit is positive and finite, and our selected series is sigma bn equal to sigma 1 by n square is a p series with p equal to 2 greater than 1, and therefore sigma bn is convergent because p is greater than 1. So limit of an upon bn as n tends to infinity is positive and finite, and sigma bn is convergent. Therefore by the limit comparison test, sigma an is also convergent. So in this way we can use limit comparison test to decide the convergence of a series with positive terms. For that we have to select another series with positive terms, and then we have to find out limit of an over bn as n tends to infinity. So there are three possibilities. Limit is c, which is positive, limit is 0, and limit is infinite. So if limit is positive and finite, then if sigma bn is convergent, sigma an is convergent. If sigma bn is divergent, sigma an is divergent. If limit is 0, then if sigma bn is convergent, then sigma an is convergent. And if limit is infinite, then if sigma bn is divergent, sigma an is divergent. So in this way we can decide the convergence of positive term series by limit comparison test. So this is all about this lecture. I hope you like this lecture. Thank you very much.